So how's the solar panel project going?
We had to change around our design a little bit
Uh-huh.
because, as I told you last week, we were thinking about using germanium, but that's too expensive, right?
I figured that was probably the problem. I didn't know what the price of germanium was relative to silicon, but there's got to be a reason always why
It's like,
people aren't using
yeah,
it, you know.
yeah. Well, germanium's like 2.5 times more expensive than silicon.
Probably only produces a marginal increase in electric.
Yeah, and sorry, I'm sick, so I'm gonna be coughing a lot.
Well, that's all right. No need to apologize for that. Better online than in person.
Yeah, especially when you're around sick people.
No, that's why I say better online than in person.
But hold on, let me get something out that we can go. Okay, so can we go? Actually, it's kind of around the same stuff as last time.
Okay.
So like asymptotes and stuff like that, I think. Hold on.
Are they problems you can verbalize is the question.
Yeah. Oh wait. Maybe they're not asymptotes actually, but yeah, I can verbalize them.
Okay.
Okay. So this one is x squared minus 3x plus 2 over 2x, or no, not 2x, just x squared minus x. And then you have to times that whole thing by 3x plus 6 over x squared minus 4.
Whenever you see problems like this,
Yeah?
it's a factoring problem.
Yeah.
Notice that we can factor the top left numerator, the top right numerator, the lower left denominator, and the lower right denominator. Let's do it, and we'll end up with a bunch of linear terms, and then we can cancel wherever they're the same. So factor the top left.
I got x minus 2 and x minus 1.
Factor the bottom left.
Just x and then x minus 1.
Factor the top right.
The top one is 3 and then x plus 2.
And the bottom right.
And x plus 2, x minus 2.
Now cancel where you can cancel.
The x minus 2's.
Whoops, hold on, what happened? I meant to do that and that, okay.
Okay, x minus 2's, the x plus 2's.
Now when I cross it out, I'm really replacing it with a 1.
Yeah.
Not being replaced with a 0, just so you know.
Yeah. And then, and then you can do it, cross out the x minus 1's.
Leaving us with?
3 over x.
There you go. Now, just let me get a little ahead of the game here. I think you're going to be good on those.
Yeah.
None of those are going to give you any problems.
Yeah.
What if you ran into this? Can you do anything with that?
You factor out the minus 1 of the bottom one.
So what's this whole thing equal to?
So it would just be minus 1, right?
Yeah. And that's the toughest you're going to run into. In other words, yeah, most everything you're going to run into. The only thing you can cancel are things that look exactly the same. But
Okay.
this is one of the rare exceptions where you have A minus B divided by B minus A. That's always minus 1, and you want to pick that up.
Yeah.
Sometimes you will run into that.
Okay.
I'm guessing. In other words, it depends on the degree of difficulty they're going to give you.
Yeah. Here, ready for another problem?
Yeah.
Let's go over, can we do 4 over 2x squared plus 7x minus, or plus 4. Oh, wait, no. Plus 5. Sorry.
Okay.
And then you add that to...
Add?
Yeah, plus 5x over x cubed plus x squared.
Just like that?
Yes. Yeah, that's it.
All right. If we factor the lower left, what do we get?
Oh shoot, I haven't factored that. Do you get...
Well, you get 2x and x.
Yeah, 2x and
The
x.
signs have to be plus and plus. And clearly it's going to have to be 5 there and 1 there in order to produce a middle term of 7x. The middle term always comes from the inside multiplied together, the outside multiplied together, and add those two together.
Wait, but wouldn't it be x plus 2, not x plus 1?
It's got to be factors of 5.
Yeah. But doesn't it have to... So the not the AC method, hold on. Well, isn't there another method where you multiply 2 times 5 and that equals 10? And
First of all, there's only one correct answer.
yeah.
So you're right. There are other methods. There are lots of methods for factoring. And I'm not really up on all of them. To be honest with you, I don't really like the California method. I don't like the diamond method. I like my own method.
Yeah.
My own method is simple, straightforward, a little bit of trial and error, but so are those methods. The difference is those methods are confusing and complicated and nobody remembers them.
Yeah.
So that's why I have my own method. Now, I know this is correct.
Yeah, that is correct.
Because it's got to be 2x squared. I separated the 2x squared into 2x and x.
Yeah.
And it's got to be plus 5. So the only term I really am wanting to check is the middle term. And you always get the middle term by the inside and the outside.
Yeah, okay.
The inside is plus 5x, the outside is plus 2x, they add to plus 7x. That is the correct factor.
Yeah, it is.
Okay.
Sorry.
Now, that's all right. Plus, let's factor the bottom.
Oh, that one? So x and then x squared plus 2x? Or should we take out an x squared?
That's the way it factors. Oh, excuse me. My apologies.
And then...
That's
yeah.
the way it factors.
Yeah.
Okay, you want to take out the greatest common. And it matters because now that we're adding two fractions, we need to find a least common denominator.
Yeah.
Well, what is the least common denominator going to be?
The least common denominator is probably going to be 2x plus 5 over x plus 1.
Not over.
Or not over, yeah, they should just, it should just be 2x plus 5 and x plus 1. Or it should,
Here's the thing. Normally, you can always find a common denominator by multiplying everything together, both denominators.
okay, I see what you did.
Okay? So if I had 1 over a plus 1 over b, I know the common denominator is going to be a times b.
Yeah.
Okay? Well,
Okay.
sometimes you don't need to do a times b if you have a common part of the thing. In other words, we only need to do x plus 1 once. We don't need to do it x plus 1 times x plus 1.
Okay.
But everything else I do need to do. In other words, I need my least common denominator to have a 2x plus 5, to have an x squared, and to have at least one x plus 1. Now, how do I know that's the least common denominator or whether that's even a common denominator? Well, if each of the denominators divide into that evenly, then it's a common denominator. And you'll notice that if I take this term right here and divide it into my denominator, I get x squared.
Okay.
Okay, so if I put 4x squared there, then I have not changed the fraction, and that's the key. In other words, always be checking means make sure that is exactly the same as that. And the way I've written it, it's really easy to tell that it is. Because I could cross off this x squared with this x squared, and I got the same thing I started with.
Yeah, okay.
Okay? So when you're doing these complicated least common denominator problems, don't multiply those two things together, ever. Leave them factored.
Okay.
And one of the reasons is that it allows you to check your work immediately. Now, I know this one has to be the same thing. And what does this numerator need to be?
It needs to be 5x and then parentheses 2x plus 5 and parentheses and then x plus 1.
Good. That's all you need to know. It's because now you can definitely tell that that is the same as that because I could cross off the 2x plus 5 and I would have the same thing I started with.
Yeah, and I forgot that the x plus 1 was already there on the bottom.
That's all right. Okay. That's the reason I do it like this. In other words, I write it exactly the way that I wrote this for a reason. I don't want to multiply the denominators. I'm going to need to multiply the numerators just because I'm going to need to simplify the numerators. So my common denominator, my answer, which I'm always going to leave unmultiplied. In other words, that's going to be part of my final answer. Now, what's the numerator? I got 4x squared plus what?
Plus 5x, and then 2x plus 5.
Multiply those two together.
Oh, so okay.
Sometimes you need to, and in numerators you usually need to.
Yeah, 10x plus 5, right?
10x squared.
10x squared.
Plus 25x.
25x, okay.
Okay. Now, the reason I needed to multiply those together is because I can simplify the numerator. I can't do anything with the denominator by multiplying those three factors together. Doesn't do any good. But the numerator, all of a sudden, I've got 14x squared plus 25x. Okay?
Okay.
So that's what my new numerator is. And I can factor something out of that numerator. What can I factor out of that?
Well, you can do 7 and 5.
No,
Well,
there's no greatest number factor, but there is an x. In other words,
yeah.
first of all, let me make this point. It only does any good to factor if I can cancel something with the bottom term.
Yeah.
And I can take an x out of that numerator. And that x, I can divide both top and bottom by x, and I can simplify this whole thing. Here's my
Okay.
new numerator. With me?
Yeah.
Here's my original denominator. But now I can cancel that x with that exponent.
Okay.
My final answer, and it's final only if I know I cannot simplify it. And it's perfectly acceptable to leave the bottom exactly like that. In other words, you don't need to multiply the bottom together.
Okay.
Okay? Now, if I could factor the numerator further and possibly pull out a factor that was in my denominator, I would want to do it, obviously. But first of all, I can't. There's no greatest common factor that I can do. And after a while, you kind of give up looking for that because you never find it. I mean, I hate to say that, but in 8 years of tutoring, I never find something. In fact, this is one of the rare times where we were actually able to factor an x out of the numerator and cancel it with one of the x's in the denominator.
Yeah.
So this is a rare occurrence.
My teacher's a toughie.
Yeah. So
Makes
what
tough.
else you got?
Let's do negative 3x over x squared minus 5x minus 14. And then minus x minus 1 over x squared minus 4.
Okay. Again, when I see a quadratic on the lower left denominator and I see difference of perfect squares on the lower right denominator, I know it's a factoring problem. Okay, and the reason it is because I can't automatically assume that the product of these two things is my least common denominator. It might not be. I might not have to make it that complicated.
Okay.
Factor the lower left, what do you get?
X, and then is it it has to get to 5x, right? Isn't that crap? I can't do these very.
I use a method that's probably different than one you've been taught.
Well, yeah, I know the one you.
My method is I need factors of 14 that subtract to the number 5. That's it.
Yeah.
That's simple.
So 7 and 2.
7 and 2. Now the 7, the higher of the two factors, goes with the sign of the middle term. So the 7 goes with the minus sign.
Okay.
The 2 goes there.
Yeah. Okay.
Now, we can be relatively confident that the right denominator is going to have one of the factors common with our left denominator.
And that's going to be x plus 2.
Yeah, only because they wouldn't give us this problem otherwise.
Yeah, exactly.
In other words, it wouldn't necessarily have to be like that, but it's always going to be like that when you get a problem like this. So now, and I really can't stress how important I think this step is. Doing it exactly this way.
Yeah, okay.
What my common denominator is.
The common denominator is going to be x minus 7, x plus 2, and then x minus 2.
Good. So I'm going to write that on both spots, like this. And now when I figure out my numerators, I will very easily be able to see whether I'm making a mistake. So the first thing I know I'm going to need is that 3x. What else goes in the numerator?
X minus 1. Right?
X minus
Oh, wait, no. Never mind. It's x minus 2.
Okay.
Sorry, I was...
In other words, the key is the moment you do it, check to make sure that it's the same.
Yeah. Sorry, I was getting a bit...
It's really easy because all you have to do is cross off those x minus 2 and you're looking at the same thing you started with.
Yeah, and I was getting a little bit ahead of myself with that.
To me, that's the easiest way to do that. I mean, there's a more technical way to do it. The more technical way is you take this term, divide it into your common denominator, multiply it by your numerator, and that's what you have. But that's quite complicated, and this is easy. So, and I know that over here it's got to be x minus 1 times something. What's its times?
X minus 7.
All right. Now, which one do I have to multiply out? The numerator or the denominator?
The numerator.
Correct, because when you operate on a fraction that has the same common denominator, the only thing you operate on is the numerator.
Yeah.
So I don't need to simplify the denominator, but I do need to simplify the numerator, and that's going to require me to multiply these two terms on the left together and these two terms on the right together. And let me express something very important here. Always remember that when subtraction is involved, you are subtracting the entire numerator.
And you distribute it. Right?
Well, what I did was I put brackets around it. And you'll see why. First of all, multiply the top left together. What do you get?
Negative 3x squared minus 6x.
Plus 6x.
Yeah, plus 6x.
Okay. Now, I'm going to put the brackets there. Multiply x minus 1 times x minus 7. What do you get?
You just get 7. So it would just be negative x squared minus 7, right?
Hold on. Don't include the negative sign. That's a subtraction sign. In other words, work within the brackets. It's the way to avoid mistakes. You don't want to include that negative. You don't want to distribute that until you've multiplied these two things together.
Okay.
Very important to multiply these two things together before you distribute the negative sign. So what's x minus 1 times x minus 7?
7.
Multiply it. FOIL it.
Oh, the whole thing is x squared and then minus 7x.
Keep going.
And then minus 1x.
X minus 8x. Okay. And what's the last term?
And then plus 7.
Okay. Now notice why I put the brackets there.
Yeah.
Had I not put the brackets there, I would get a different answer. The brackets tell me that this negative sign has to be distributed to every term that is in that brackets. If I did not have the brackets, I would end up with a plus 7, whereas in reality, I'm going to end up with a minus 7.
Yeah.
Now, let's simplify the top. Remove the brackets. What do I have left?
It's negative x squared plus 8x minus 7.
Now simplify. How many x squareds do you have?
4x squareds. Actually 2x squareds.
No, it's
No, it's 4.
minus 4x squared. How many x's do you have?
You got 14 x's.
And the total number?
And then plus 7, or minus 7, I mean.
Minus 7. And all of that is still over our common denominator.
Yeah, okay.
Or really our least common denominator. You're dealing with variables. It's fair to call this the least common denominator. Now, again, I face this 100 times a year and I've never found it. In other words, when you get to this step, you have to be thinking, well, what if I could factor the quadratic on the top and end up with a factor that was on the bottom? Then I'd be able to cancel it out, and I would need to do that to simplify it. But, gosh, not once in 8 years have I ever seen it to be the case, and I've wasted all that effort to do it.
Yeah.
Now, there's a little bit of a shortcut. First of all, the only possible factor that could come out of the numerator that would match the denominator would be which one?
X minus 2, right?
No, there's no way. 2 is not a factor of 7. Remember, those two numbers have to multiply to 7.
Yeah, it would be x minus 7.
X minus 7 is the only possible one. Well, what would that force the other one to be? 4x
minus
plus 1. It doesn't work. Okay, or does it? Let's see. What's the middle term? That's plus 28x. The last term is minus 1x. That would give us a middle term of 27x. That's not our middle term. So that does not, the numerator does not factor into anything. It might factor, but it does not factor where one of the factors matches one of these factors in the denominator.
Yeah, okay.
The only one I really need to check is the x minus 7, because there's no way x plus 2 or x minus 2 could come out of that factoring. X minus 7 might. If the other factor were minus 4x plus 1, that at least produces the minus 7. Okay? And but when I check what the other one would have to be, it doesn't work. So that numerator does not factor, as it never does. And this is your final answer. One of these days, I'm going to find it factors, and I'm going to be able to cancel it, but I haven't yet. All right, what else?
Let's go, wait, hold on.
So is germanium the best element to use in a perfect universe if you had all the germanium that you could get your hands on?
I mean, maybe, but we're gonna experiment with something else. We're gonna experiment with gallium.
Oh, okay.
Because
I also know a little bit about the lens that you can put above the solar panel. There is a type lens that focuses the sunlight and gives you effectively twice as much light on a given piece of area.
We were thinking about having our solar panels kind of like a solar concentrator, you know?
Well, that's kind of what I'm talking about, is that if you put a lens above the solar panel, it actually takes all the sunlight coming in and focuses it.
Yeah,
applying more sunlight to your solar panels than would normally come in.
But
hold on, that's also expensive.
Yeah, but hold on. Let me explain our design really quickly, because our design would kind of be like, on the inside, it would kind of be like a bowl of mirrors, right?
Okay.
And it would, all those mirrors would be concentrating onto kind of like a pillar that extends up, kind of like at those farms, you know, that you see in like the desert and stuff.
Right, right. No, the most efficient on planet Earth, the most efficient solar panel collection is actually where they all reflect onto a bowl of water that's heating up. And you take the steam from that tank of water
Yeah.
and apply it. That's the most efficient solar
And,
panel and
yeah.
electricity on the planet right now. Better than
Yeah.
PV panels.
Yeah.
So it sounds like you're halfway towards that.
But we were, instead of having it heating up something, we were just going to have solar panels on the pillar, right?
Mm-hmm.
And so, well, what we found, at first, actually, what we were thinking was, like, the hotter it gets, the more energy there is, right? Because that's kind of like how thermal energy works. And the more energy it's going to produce, but that's not what we found. That's not how it works. Because the hotter the solar panel gets, the actually less efficient it
Less
gets.
efficient it becomes, yes.
Yeah.
It's all about how much sunlight there.
Yeah.
And
So
the cooler it is, the more efficiently it operates, just like any engine. Any
yeah, like
engine operates more efficiently if it's cool, not hot.
Yeah, like a computer. So we were thinking to solve that problem, we were just going to have like, I don't know, have you seen those water heaters that they put, or water coolers, I mean, that they put in computers nowadays?
No, I have not.
Well, they have like this little pump and a little reservoir and everything that they put inside of your desktop.
Really?
And they have these things filled with antifreeze. But we're going to use just deionized water because deionized water is completely not...
So they reach their maximum point of cooling using air fans, huh?
Yeah, basically. And
those don't work at the level of heat that the new computers produce.
Oh, yeah, no.
So
but
those... come up with a new solution, and that's what it is.
But this is like... But we were thinking we would have like a little like area where there could be a large fan keeping this reservoir cooled at the same time when it's pumping all of this water through all of the solar panels, and that would keep them cool.
Huh.
And I guess gallium, I was looking at it, and my friend is also, he's like in AP chemistry and stuff, so he's pretty good at chemistry.
Mm-hmm.
And we were looking at it, and I guess gallium has kind of the same attributes as germanium.
Yeah.
Except for its melting point is way lower. Its melting point, like, it can melt in your hand. It's really low.
Huh. Wow. Now, the method I was talking about, just in case you're not familiar with it, is say you have a solar panel like that. Right above it, you put one of these lenses, and I can't remember the exact name of that lens. It's a frenetic lens or something like that. Whereas all the sunlight that comes into that gets focused onto a central point, which means you really only need a solar panel that's not that big, but like that. Okay. Yeah. So normally this solar panel would collect normal sunlight, but now this particular lens concentrates all that solar panel onto that.
Yeah, that's what we were thinking. We were thinking that we're going to have a lens over the top of the whole thing.
Right, exactly.
That also, not on top of magnifying it, it can refract the light too. Huh. So and like with refracting it, I think that might solve the problem of like when the sun goes around, you know, like maybe you can just have it on like a flat piece.
Well, where this makes a lot of sense is in outer space.
Oh.
Not so much on Earth, but of course all solar is going to be better in outer space because you get 24-hour sunlight.
Exactly.
but I seem to remember there's something special about these lenses that they would be more effective if they had sunlight 24 hours a day. Although that's true of all solar panels. So I'm not sure what it was about this. Anyway, I don't want to distract us too much from your math.
Yeah.
So you are working on a project that is dear to my heart.
Yeah, getting me like talking about my solar project. But I was actually, shoot, what was I gonna say? I can't remember. Never mind. But here's one problem that we can go over, and it's 1 minus x over x squared divided by 2x plus x minus 3.
And it's written like this, right?
Yeah.
2x over what?
2x squared plus x minus 3. And that's over 2x squared plus 3x.
Alright. Important to recognize what this is. This looks like a division problem, but it's not. It's a multiplication problem.
Yeah.
Okay? So the very first thing I'm going to do is turn it into a multiplication problem.
Okay, so you're going to flip it?
I'm just going to flip it. And now it's just as simple as the other ones we've been doing. So anything that looks like a division problem, always remember it's really a multiplication problem. And immediately do that. Now, factor wherever you can factor. Well, I can't factor the upper left. I can't really factor, well, I can kind of factor the lower left. I can turn the lower left into x times x. That's going to help because what happens when I factor the upper right?
When you factor the upper right, it's going to be, you factor out the x, so it's going to be x and then 2x plus 3x.
Just plus 3.
Or plus 3, yeah.
Always be checking. Again, whenever you factor anything, the very first thing you should be doing is multiplying it back together again to make sure you got what you started with.
Okay.
That way, you know, if you wait till the end of the problem, well then you've got 4 sub-steps that you got to check if you don't have the right answer. And sometimes it just becomes impossible to go back and figure out where your mistake is. But if you're always checking at every step, then you'll pick up mistakes. And that, believe it or not, is one of the big secrets of math, is catching your mistakes when they're catchable. It's the rest of that on the bottom right.
Will it be plus 3 and then plus 1?
Well, first of all, that tells you the signs have to be opposite.
Yeah.
There's no way they can be the same and produce a minus 3.
Okay, so
it's got to be a plus 3 minus 1 or minus 1 plus 3.
I think plus 3 minus 1.
Now, the only thing I have to check is the middle term. Does that produce the correct middle term?
Let's see. So 2x.
You don't need to check the 2x. In other words, when you're checking the middle term, you're going to do the inside and the outside.
And that does equal x.
Does equal x. And that's all you need to check. Because if you factored it the way I factor it, you know the first term is correct and the number is correct. The only thing that we're not 100% sure of is the middle term, so you always check the middle term. Now, since multiplication is happening, this becomes really easy. It's not a least common denominator problem. It's a cancel where you can cancel. And I see that we've got a factor here that we can apply what I told you about. What's the first thing we can cancel?
The 2x plus 3, those things.
What else?
X, wait.
One of the
yeah, we can
one of
cancel
the
out.
x's. What that leaves us in the numerator is this, and what it leaves us in the denominator is that. And always leave these things unmultiplied together in the denominator.
And then can't you factor out a -1 on the bottom too?
So what's the answer?
So it'd be negative x, right?
-1 over x, and they are not the same thing.
Oh, okay.
In other words, the x stays, in other words, I'm going to cancel that out with that, but I've got to put a -1 in there.
Mm-hmm.
Otherwise, I can't do that. And now what I'm left with is -1 over x, but not the same as -x. You got to make sure you get it in the denominator or the numerator properly.
Okay.
Yeah. All right. What else you got? And this was the first case we've seen where we had a 1 minus x and we also had an x minus 1.
Yeah.
In other words, this is the first problem we've seen where we could cancel stuff out that was not exactly the same as one another. And that's the only two things that I can think of that you can cancel out, is where they're exactly the same, or if one is a minus b and the other is b minus a.
Okay.
Okay. What else?
Well, actually, no. I have a question. Sorry, we're going back to the solar thing. But I have a question about that lens that you're talking about, where it magnifies the light. Do you know if like it magnifies light, kind of like how water magnifies light?
I don't. There's a certain name on this lens. And it basically takes all of the sunlight. In other words, it's got a semicircular shape like that.
Yeah.
And the reason is that all of the sunlight coming in as vertical lines, you want it to come out like that. Because underneath this lens, you only have a solar panel that's that big.
Yeah.
So you have a lens on top of the panel that's actually bigger than the solar panel. But it basically accomplishes the same thing that a solar panel that was that wide would accomplish.
Yeah.
Now, the name of this lens, there's a very special name of it, and gosh, it's been 8 years since I've really done much studying on this. The only term I can think of is frenetic, and I know that's not correct, but it's something that sounds like that. You might do a Google search on lenses above solar panels and figure out what it is. But it's a type lens that is built in a way that it focuses inwards and it focuses all of the sunlight onto a smaller panel, and effectively that gives you more sunlight per square inch.
Yeah, okay.
And I seem to remember that it would be most effective in outer space, but I'm not sure why. In other words, there's a reason they use gallium or germanium in outer space. Yeah. They don't care about the cost. They're looking for the most efficient material in the universe. Yeah. The biggest cost is putting it in a rocket and getting it to outer space. Yeah, they don't care about the cost of the material, the germanium or the silicon. That's not the major part of the cost. So they go with what's most efficient. Okay. So it really matters whether you're talking outer space or most efficient or a biosphere maybe where you would want the most efficient. Or top of somebody's house.
I was thinking that as a part of the design, I don't know if this would actually work, but maybe you could get like two birds with one stone and cool it down and also be magnifying the rays at the same time, because I was thinking that in order to cool it down, you have water going over the face of the solar panel, like with direct contact to like actually all the like
Maybe
all
that's
this.
why this works in outer space, is because you don't have to worry about cooling it.
That's true.
Maybe.
'Cause,
Yeah, because I had never thought about that. So you're saying that all of this concentration of the light is going to heat up the solar panel and reduce its efficiency.
exactly, and that's also what we were thinking with the cooling. And with the cooling, maybe if you run and also if you run water down the face of the solar panel with direct contact, hopefully, I think it'll cool it. And also because it's deionized water, it won't like react with any of the electricity going on.
Do you have any solar panels? Or do you have a kit or anything like that? Or does your house have panels on them?
No, but I want to. I want to buy a solar panel.
I have a nephew that he got a Christmas gift once that was like a $500 solar panel. And it was just a little portable one that he could take up camping with him
Yeah.
and set it up next to his tent, and it would provide enough electricity to run his TV or telephone or something. I don't remember, but that got him started, and that turned on something, and a year later he had solar panels all over his roof. And that was really exciting for everybody. I think it should be a law that every house in America should have solar panels on top.
Yeah, and they're just, it's like saving money, honestly, too.
Well, and it overcomes the problem of establishing solar farms where you have to then build up the grid to get that electricity to where it's needed.
Yeah.
If everybody has solar panels on their roof, it's like everybody has a little mini power factory.
Yeah, and also there wouldn't be
as needed right there.
And there wouldn't be as many like blackouts or anything.
Right. Well, and that's even better, although that's another step. Most of the time nowadays, when you get solar panels on your roof, they will not operate independently of the grid. In other words, if the grid goes down, your solar panels don't work, you have to put in like a $5,000 converter.
Yeah.
That converts it so that you can directly use that electricity.
Yeah, I'm just thinking like in the future, hopefully, like hypothetically, when everyone has one.
It still works the way it's set up now, because by law, all of the power factories have to pay you for any solar energy you produce, and have to let you feed it back into the grid. So it's just as good to put solar panels on your roof. It's just that they wouldn't always provide electricity in case the grid goes down. And I'm with you. If I had solar panels on my roof, I would want them to work if the grid goes down. That's part of the reason I would want them up there in the first place.
Exactly.
Because there's a high likelihood that the grid will go down in the next 5 years at some point.
Exactly. There's always blackouts. But also with this water thing, the water magnifies the light, right?
Yeah, probably would. If you put water in between this lens and the panel, it might magnify this light even more. I don't know. I don't know. But
well, I know that like that's one of the things, right? Like if you stay in water, it's like...
Well, it's going to affect the temperature, which affects the efficiency. So you got a lot of factors that are affecting how much electricity this panel is going to output.
Yeah, it's like...
Part of that is how much light comes in, and part of it is how hot the panel gets. So there's probably a perfect combination of lens and cooling that give you maximum output per square inch of that solar panel.
Okay.
I'm not quite sure why all of the panels on Earth do not have these lenses on top of them.
Do you know if there's anything special that goes into them?
I don't. Like I said, I can barely remember the kind of name. It's a special kind of lens, and I can't remember quite what is special about it. But obviously it must be expensive, or everybody would have one of those over their solar panels. You know, if it increased the electrical output of the panel, you'd get it unless it was prohibitively costly.
So basically what you're saying, this lens is kind of like a contact lens almost? Like it magnifies
Well, see all these vertical rays coming in? That's the sun. And
Yeah.
what this lens does is it redirects those rays towards a central point. In this case, that solar panel.
Okay.
So this solar panel gets the equivalent of 8 inches of sunlight in a 5-inch panel. So it increases the electrical output of the solar panel based on that, since the output is pretty much a function of the amount of light coming in and probably the temperature of the panel. And maybe that's the problem with these lenses, is it may heat it up so much that it loses the effect that it's desired. And maybe that's why it works in outer space, because there isn't a heat problem up there.
Yeah, exactly.
I don't know, but
Maybe that heat problem is actually like a really big thing holding back solar.
is it really? So the hotter it gets, the really much less efficient it gets, huh?
Yeah, that's what I'm thinking, but I don't know. That it might not be the case.
Because the state-of-the-art technology now is to have a tank and have a circular array of panels that are all directed to that tank. And that tank's full of water, and you're merely heating that thing up. So all the solar panels now reflect the sunlight onto that tank, and then that tank boils, produces steam, and that's what produces the electricity.
Well, I don't even think those are even solar.
For are
those even
right now?
Are those even solar panels, or are they just mirrors?
They're just mirrors. You're
yeah.
Right. They're not PV solar panels. They're mirrors.
Well, maybe you could honestly make those into solar panels because silicon is really reflective.
Huh. So you're saying maybe they could be both. They could reflect. Yeah. They could reflect the light onto that tank of water, and they could also produce electricity.
Yeah, and collect a residual amount of like electrons. And
the only thing I know is that there's laboratories all over the world that are researching each of these things that we're talking about.
Yeah.
And somebody knows the answer to them already.
Yeah.
It includes, you know, what material to use, germanium or silicon, whether to use mirrors, whether to use solar panels, whether to use tanks of water. All of that has already been analyzed to death, and that's why I say this is the state of the art. If they build a solar farm in Southern California, this is the way they do it right now.
Yeah.
It's just mirrors reflecting light onto a tank of water.
That spins a motor, basically.
Yeah, well, the tank of water boils, producing steam, and the steam spins the motor. And when the motor spins, it produces electricity.
Yeah. See, my brother was also giving me, Lucas, right?
Uh-huh.
He was giving me an idea, and he was telling me about these skirts under cars.
Uh-huh.
That I guess have these little rotational kind of like turbine things almost. And it would basically, he was basically going like, you can create solar and wind because you can have these things that condense like air or wind, and then they can go underneath these skirts that spin these turbines and make electricity maybe.
Huh. Haven't heard that idea. Sounds interesting. I'm always interested in technology of the future or the present. So be it, you know, if somebody thinks of it.
Yeah, exactly.
But yeah, it's real interesting stuff. So are you planning on trying to be an engineer yourself?
Yeah, like maybe a chemical engineer.
Uh-huh.
And I'm going to try and get into the solar panel business.
Good. Good. I don't think there's a field that's The only field I can think of that might be hotter than that in the next 50 years would be cybersecurity.
Yeah.
But
Or
those two
robots
fields
or
are
something.
not going anywhere. Those two fields are going to be around for your entire lifetime.
Mhm. Oh yeah. Or at least until fusion is made.
Well, I suppose you're right. If somebody overnight comes up with an energy source that's more efficient than solar, then it could kill the solar industry overnight, but it would
Yeah,
still benefit mankind enormously.
yeah, I don't care at that point. At
Yeah,
that point,
I
I'm
don't care
like,
whether it's solar or fusion as long as it's not burning fossil fuels.
exactly. Time to get out of the Stone Age.
Yeah, for sure. Even though we elected a president that insists upon trying to take us back to it.
Yeah, that coal thing. Oh my god. I kind of laughed at that, honestly.
Disgusting. It is. It's just totally disgusting.
Well, my dad's in the he's in the oil and gas business, and he goes, no way he's not going to bring any coal, I need jobs back to the coal market because natural gas is just
Right,
killing
right. The
the farm.
prices, it's not, even without regulation, coal could not compete with natural gas.
Oh yeah, it's just,
That's where it's at. Thank goodness.
even oil is having trouble
Right,
competing with natural
right,
gas.
right. And that's partly why the price of oil and coal have plummeted over the last few years. It's
Exactly.
because natural gas, they figured out how to produce it cheap with fracking, and
Hmm.
it's even without it being cleaner, it would be cheaper. But the fact that it's cleaner also just makes it just too appealing. And
Yeah, it's just way
coal
better.
can't compete. So regardless of what Trump does, coal is not coming back anytime.
And if anything, that's also going to hurt him. Like, he's promising all this stuff, and it's like, that's not how economics work, dude.
Thank goodness. Thank goodness that's not how
Actually,
economics works. Because, yes, maybe economics will save us from ourselves.
I think it might have been on the stock market somewhere, but the stock market is actually like starting to actually say that climate change is a huge threat to like the
Yeah,
economy
no,
and stuff.
no. All intelligent people. I mean, eventually everybody has to come around.
Exactly.
It's only the Stone Age people that, but you know what it is? It's people that have vested interests. And if
Yeah.
you're a coal miner or if you own a coal company, then you're going to be making the argument that coal is where it should be at. And
Mhm.
that's really what it kind of comes down to. And you got to be careful in life because it all comes down to all of the vested interests. Oil
Mhm.
oil companies want oil to be made. Coal companies want coal. Solar companies want solar.
Mhm.
So, and everybody's always working in their own best interests, and you got to be careful. It messes with the truth.
Yeah, and money's always involved in that.
Right, right.
Yeah, that's what you're
What
talking
if
about.
coal drops so far in value that all of a sudden it becomes the cheapest energy source, cheaper than natural gas? Well, then people are going to go back and start
Mhm.
digging up coal, and
Mhm.
unless there's some sort of a regulation to prevent it. But
Yeah.
economies
But
generally
it's well, and also like I think renewable energy is just growing so fast now, not only because like climate change, because I think that's like people really like I think that's a big portion,
rule.
but I think that kind of gave it its push. And then as soon as it gets like cheaper and cheaper, more and more people are gonna
Yeah,
start to
no,
notice.
when I wanted it into renewable energy was like 8 years ago, and over that 8 year period, solar panels dropped by 60% in value, in cost rather.
Yeah, and are producing more energy.
Right, and all of a sudden, solar is very, very competitive with everything else.
Mhm.
Um, and if that keeps happening, part of that was China.
Oh yeah, China's huge in solar.
Well, and China by being huge, they knocked the cost way down.
Mhm.
Kind of destroying the solar companies in the United States in the process, but still benefiting the world greatly by making solar panels cheap.
Yeah, actually. Anyways, I don't want you to be late for your next appointment again.
Simon, it's always fun to talk about something other than
Yeah.
math sometimes.